So I've been short introduction for Mike. So most of you know Mike where. So the interesting thing is Mike, right? So I learned that Mike got his bachelor's degree from here. But not from this building, right? So this is the building, right? So you know.
Still counts.
Yeah, so 35 years ago, so I almost got a parallel career with Mike. So got my bachelor degree same year, same year for PhD, working on ARM for last how many years? 27 years. So yeah, Mike has leading, right, from my perspective, right, he's leading a lot of big events in terms of ARM. The M33, which is that bigger field campaign over the Great Plains, so that data set we still use them. Huge data sets. The challenge to get observation at the right place and right timing. Still big issue for atmospheric science. So now this on today is another new field. Other than heliosphere campaign, he has played a lot of role in high level. This is what we call ACP3 working group. So you're leading for that last almost 10 years. Right. So that is big international group working on different type of clouds, try to improve them. Now, for those working on it here, know now here is active in the cloud aerosol, and you talk about aerosol. The scattering part of lots dealing with aerosol, right? So there's a big project in the lab in the world being air and the argon. So it's long names here, so I couldn't remember, but it's a project in to keep that going, right? So, but I think that is a lot of where we could interact more with the Stony. So I'll use you more time than you go, right? So we have lunch after talk.
Okay. Thank you very much. Thank you for the opportunity to come in and speak to you today. Yeah, it's great to be back to my alma mater. I can't believe it's 35 years ago. That's kind of scary. But yes, today I'm going to talk about a field campaign that I led and some of the work that's coming out of that, looking at aerosol-convection interactions. And I will start off with a slide that you've probably seen many times that motivates a lot of the work that we're doing. So this is from my SXP report on the effective radiative forcing, and you see lots of the different forcing agents there, the greenhouse gases, changes in surface albedo and land use. But I want to point you to the aerosol part down there, which is broken down into both aerosol cloud and aerosol radiation interactions. And the thing to notice there, first of all, that it has a net cooling effect, so it offsets some of the. See, and there's some. Maybe they can't hear us. Or...
No, they're okay.
Okay. Aerosols offset some of the warming due to greenhouse gases, but you notice there that there's a large error bar on those values, and even if you can discern the two different blue colors there, the aerosol cloud interactions are a big part of that uncertainty in radiative forcing and motivates much of the work that we're doing.
Yeah.
Sorry.
Okay. Okay, so a big one of the components of those aerosol cloud interactions is the role that aerosols play interacting with convective clouds. So here I'm generally talking about deep convective clouds, and storms might be another way to refer to them. But this has been in the news a lot over the recent decades or so. where there's lots of debate over what might happen as aerosols are ingested into deep convective clouds as they're forming. There's a whole argument over whether that might make those storms stronger or weaker. And I'll tell you, this is quite a debate in the community. You should come to some of our sessions at the AMS. People are pointing fingers, yelling at each other. It's interesting with quotes on there. But I in particular, here's lots of the different things that air pollution may be fueling more powerful storms, impacts the Pacific storm track. I ended with this one on top, which showed a study that was linking air pollution from chemical plants in the Houston area and its impact on rainfall in Hurricane Harvey. Lots of work out there being done that maybe these interactions between aerosols and convection have important implications. Okay, so to say a little bit about how this might happen. So how do aerosols interact with clouds and storms? We'll start off with just the basic premise that if all else is equal, if we have more aerosols, we're going to have more smaller droplets in the clouds, right? And what that does is it suppresses the collision coalescence formation of precipitation, right? You have lots of cloud droplets that are smaller, more similar size. It's hard to get them to collide together to start to form raindrops. If we take that at its face value, start with that. There's a couple different mechanisms that have been proposed that might make storms stronger. The cartoon on the right-hand side here shows kind of what I'd say is one of the seminal papers on this now by Danny Rosenfeld. Shows what's called cold phase invigoration. In this case, as we talked about, rain formation can be suppressed in a convective cloud. Because rain isn't falling out of that cloud, more water is lifted above the freezing level. That releases the latent heat of freezing as that water freezes. That warms the air, making it more buoyant, gives us a stronger storm, stronger updrafts, more mass flux, and all the things that come along with that in a storm. I will say one major criticism of this is that the theory actually assumes that all that water falls out of the cloud as soon as as soon as it freezes, it falls out of the cloud, which probably is not what happens. So hydrometeor loading and other things probably play a bigger role than was thought of when this was first put into the literature. More recently, we've heard about warm phase invigoration. Is a very similar technique or a very similar process. In this case, though, you have more aerosols, more smaller cloud droplets. That means you have increased droplet surface area of those droplets that are formed. That gives you more opportunities for condensation. That increased condensation releases latent heat of condensation in this case. Then similar processes. Warm air, it warms the air, making it more buoyant, gives us a stronger storm. Indeed, the community in general feels like the physics here is okay, right? There's no gap in the physics, as you might say, with cold phase invigoration. But what's hard to do is find observations of the real world that show the supersaturations that you would need for this process to be relevant. So indeed, there's kind of a search out there right now for those high supersaturations you would need. Okay, so in that context, we want to go out and study these things. Problem is, right, convective clouds are a really complicated system. So this is a very nice figure out of a recent paper led by Adam Marble. And you don't need to go through all the details here, but basically you see kind of a convective cloud going through its life cycle from left to right, initiation, deepening, and then eventually a mature stage. And what they've listed here is lots of the different processes that are impacted by aerosols and that might influence the updrafts in those convective clouds. And what I want you to notice is the color coding on here. So the processes that are colored red say that they have a positive, that process has a positive impact on the convective updrafts when you add aerosols. The ones that are blue have a negative impact with more aerosols. And then the gray ones are all uncertain. And so first of all, you see lots and lots of gray. So there's lots of processes we still need to understand these links a little bit better. The other thing I note is that the arrows on there are a little bit hard to see, but some are up, means they would increase the updraft strength. Some are down, would be negative, and some are sideways or uncertain. And again, there's lots of uncertain things there. So the takeaway is it's a complicated system. There's lots of different processes we need to take into account if we're going to study this. It tells us that we probably need some combined observational and modeling approach to try to tackle this problem. And the other thing is a lot of those processes that are mentioned there are coupled. So such that, and I've grabbed a couple of quotes, one from a different paper by Adam Garvel that points out the effect of some of these cloud property changes that we're looking at, that large changes in one variable can be canceled out by small changes in some other controlling variable. In this case, in particular, he's talking about atmospheric thermodynamics and the convective available potential energy. Small changes in that could swamp the aerosol signal. And in his review paper, Wade Botal pointed out that disentangling these meteorological and aerosol effects are a daunting task. The figure here from Younggang Liu, my colleague at Brookhaven, just shows one example where he was looking at entrainment rate in this case, but it could be any other process in a cloud, and how it's linked to all these different processes that indeed are also coupled with each other. So that cross-process coupling really makes this problem even more difficult than it would be at first. Okay, so despite these difficulties, and Zen mentioned this Aerosol Cloud Precipitation Climate Working Group. This is an international, an international working group that's looking to try to address problems about aerosols and clouds and how they relate to the climate, with the goal to identify and disentangle and quantify the signals of the impacts of aerosol perturbations on clouds, precipitation, radiation by using observations and models across scales. And this group is broken into there's a whole group of folks that work on warm, low clouds. You can imagine, marine boundary layer cloud studies, things like that. And then the group that I'm involved in that indeed seeded the idea for the campaign I'm talking about today is the Deep Convective Clouds group. And what this group started off by doing a few pilot studies. So they actually, before I was even involved in the group, they looked at trying to find a region where they might expect to see strong aerosol signals on convective clouds. They identified the humid subtropical climate of the Houston region as being a good place where we have a large and diverse aerosol sources, both anthropogenic and natural aerosol sources, but also lots of convection, especially in the summertime, that give us a good setting to try to see if this perturbation may even exist. And there were a number of observational modeling studies that were done. Here I highlight, I think that the biggest motivational study that came out of this, a model and comparison project, where 7 state-of-the-art cloud resolving models were brought together. And this is one of the big plots that came out of that. This paper was led by Peter Marinesco from Colorado State. Sue Vandenhever was, say, the PI on the project. But this plot, just to orient you, shows the time on the bottom here. So this is a 12-hour time period, right? Yeah, 12-hour time period. And what's plotted is the accumulated precipitation. It's done for all the 7 different models. So each model is a different color on there. And then the solid lines are for a clean simulation. The dashed lines are for a polluted simulation. Then also I add the black line, and here's the observations. Okay, so a few things that jump out right away. First of all, the simulated precipitation varies greatly among the models. So you see this wide range of more than a millimeter in the accumulated precipitation across those models. With most of them underestimating that total precip by more than 40%. So So that suggests to us right away that, hey, there's some fundamental physics about precipitation formation and all that we need to get right in these models before we might be able to even look at these aerosol impacts on convection. But then if we look at the differences between if we do look at those differences between the solid and the dashed lines, the clean and polluted conditions, for individual models, you might be able to notice that that they're kind of all over the place. We have some cases where polluted conditions cause a decrease in the precipitation, somewhere there's an increase. So even the sign of that feedback is not consistent among the models. So lots of room, which maybe is not surprising from the convection is complicated slide before. Lots of room to improve how we simulate these things and our understanding of the processes that underpin that. Okay, so based on that, we proposed to do this field campaign called TRACER to try to collect some of the detailed observations we might need. Detailed observations in both time and space of convection and the environment that it forms in, including the aerosol properties. So TRACER stands for the Tracking Aerosol Convection Interactions experiment. Took place from October 21st to September 22nd, sponsored by the Atmospheric Radiation Measurement Facility, or ARM. We had this intensive operational period during the summer months when we get warm, moist air from the Gulf of Mexico moving over this area that's often associated with the sea breeze. That gives us lots of isolated convective cells, exactly what we needed to try to look at these interactions. One of the really cool things when we first proposed this and it was selected was there was lots of community interest to join in and help us look more closely at this. So you see here we had NASA was very interested in combining some air quality studies with this work. Their two programs here, plus the Texas Commission on Environmental Quality, put together a sister campaign looking at air quality that had both a phase in 21 and 2022. Then actually, Pablo Scoyas from Stony Brook here led the National Science Foundation work on the experiment of sea breeze convection aerosol precipitation environment, or ESCAPE. This looking holistically at these interactions, not just between convection and aerosols, but also this coastal environment. And then there was also, we're in Houston, a big urban area. So looking at the impacts of the urban environment on convection, the boundary layer, and precipitation in that area. So that was one of the really cool aspects. All of a sudden, this blew up into a much larger campaign that helped. These helped fill in some of the gaps we had in our measurement science, but also expanded the science we were looking at. I'm only going to talk about the DOE component today, so just for the amount of time we have. So I'm going to focus on these two parts of it, and mainly the intensive operational period. I'm going to tell you a little bit more about what we did out there. So I mentioned these dates already. Here's a map of where we were. So we had, first of all, the ARM mobile facility, which this is a pretty significant facility that includes more than 60 instruments, really state of the science measurements, collecting observations of the clouds, aerosol radiation, meteorology. This was deployed up here in LaPorte, Texas, which is near the shipping channel just off of Galveston Bay there. This is a very highly polluted area, lots of industry, lots of transportation, not far from the urban area. This was our main polluted site. Okay, here's another picture during installation of the site, gives you an idea of the scale of this. So several sea containers, as many as I think 10 different sea containers that include the instruments, the data systems, everything associated with that. And we also had this string of instruments. You see several microwave radiometers lined up here, but this went out further, collecting additional radiation, meteorology, precipitation, flux measurements at this site. So this site was operating 24/7 over the entire year, collecting these data. It's all all that data is freely available in the ARM archive. Okay, one of the really unique aspects was at the site, about 30 kilometers away from the main site, we deployed the C-band scanning precipitation radar. This is a research grade radar for looking at formation and propagation of precipitation cells. What was special about this was we deployed a new automated cell tracking capability so that using unattended software with that radar, the software would identify convective cells that we wanted to track based on a set of criteria, and then it would follow them scanning at high resolution. So we could really look at the evolution of the convective core at the time scales that we might be able to look at some of this evolution of the microphysics going on in the precipitation core to look for these aerosol signal or the signals we might expect associated with aerosol invigoration. I definitely want to point out that software was developed here and at Brookhaven. So Pavlos and Ed Luke and several others were the ones who developed that. And it worked really great, great demonstration of that new technology during the campaign. And finally, to the south and west of the city, we had what we called our ancillary sites to capture the rural aerosol and thermodynamic characteristics. Think of this as the background site that much less pollution in this area, less urban influence. So we wanted to be able to understand that contrast between the polluted and the non-polluted area. Interested just to, so this is mainly an aerosol trailer and some meteorological measurements. This big circus tent looking thing housed the tethered balloon system. So we did a bunch of measurements in the lower atmosphere of mainly aerosol, some trace gas measurements and meteorology from that tethered balloon system. Okay, and there's a little bit closer look at that. So yes, just to remind you, here's our mobile facility up here in a polluted region. This is our ancillary site, capturing that background state. And this was where the radar was, such that it could observe convective cells going over each of the sites, kind of at just the right distance away to observe the freezing level microphysics. Okay, so that's our experimental setup. So what I want to do now is talk a little bit about the work that we've been doing at B&L to get at these, maybe starting to understand these aerosol convection interactions. And to do that, we really need to look at multi-scale influences on convection, because it's not just going to be those microphysical processes we care about. Well, you need to understand what the larger scale meteorology is. So we're going to look at, we've got some work looking at these different scales, from understanding the synoptic regimes that the convection's forming in, to the Gulf and Bay breezes or the sea breeze interactions that drive some of the dynamics that forces these convective clouds. Then I'll get a little bit into the aerosol convection interactions, both a causality analysis using observations and some modeling work that's being motivated by the ACPC work we did before. Okay, so just I don't think this audience needs too much on this, but I'll go through it quickly. Of course, if we're thinking about convective clouds, and this is a nice convective cloud picture I took while I was out in the field. You see, here's some of the aerosols being generated from the refineries and industry in that area. And this was actually a nice cell that was starting to grow along the Bay breeze front as it was moving towards our site. But that cloud is impacted by many different scales. And I started at the synoptic scale. So it's a large scale synoptic meteorology is driving the low and high pressure systems in the area. And that large scale ascent or descent associated with those synoptic motions is going to give us conditions that are suitable for formation of deep convection or maybe suppressing to that. So first thing we wanted to do is be able to characterize that large scale. Of course, the second thing, we're in this coastal region, not far from the Gulf of Mexico, the Gulf of America. And indeed, the sea breeze circulation is an important driver of what's the convective formation and indeed the regional environment in that area. Of course, in Long Island here, we're well aware of these sea breeze circulations. They drive our weather, especially in the summertime here all the time. So we wanted to characterize the influence of that sea breeze circulation on the clouds. And then, of course, the local environment that convection forms in, things like the humidity, the temperature that drives the convective available potential energy, and the buoyancy available for those updrafts. Okay, so I'll start off with this work led by Dia Wang from Brookhaven, and I will mention her name a lot. She's been working closely with me on a lot of this. So what she did was we wanted to use the long-term record to understand the main synoptic regimes that we experience in this Southeast Texas region. She applied self-organizing maps to more than 10 years worth of summertime Era 5 700 millibar anomalies. So she applied this machine learning technique, and what came out of that was that we see three dominant synoptic regimes, and of course one that's kind of a transitional state between those that really are the main regimes we see in this area during the summertime. Those were a pre-trough and a post-trough regime, as we see indeed, especially towards the beginning of the summer and the end. We often see frontal systems moving through this area, whether they may be a little bit weaker during this time of the year. But by far the largest driver was anticyclonic or high pressure in that area that drives the formation of the sea breeze, right? Because that large scale synoptic regime will generally have clear skies during the day that will help enhance the land sea temperature contrast over the course of the day, drives the sea breeze, gives us that boundary that helps us form convection. And indeed, we saw as we looked closer at sea breeze formation that we see most of those sea breezes forming in this anticyclonic regime. On the bottom right here is just a simple bar chart that shows the frequency of occurrence, or actually the total counts during the 4 months of the campaign. And nicely, once in a while, when you do a field campaign, things happen like you want them to. And the anticyclonic regime, which is going to give us those isolated convective clouds, was the dominant regime that we saw. Yeah, but that helps us put each one of our convective clouds into context. We start looking at some of the smaller scale aerosol convection interactions we can control for this large scale forcing that we might experience. Okay, secondly is the impact of these Gulf and Bay breezes. So some work again that Dia Wang led was to really identify when our measurements are being impacted by the passage of that sea breeze front that's associated with the circulation. So she used a combination of satellite visible reflectance that would be associated with the clouds that form along that boundary, radar reflectivity, mostly the precipitation, but maybe other insects and things like that the radar signal can be reflected by. And then our surface meteorology measurements, where she applied what's called a change point algorithm, but basically looks for gradients in the surface meteorological measurements that would be associated with this transition in air mass from the continental to the maritime air mass. Looking at our site at La Porte, or the main site, she identified 48 passages of the sea breeze circulation at that site. And then we started to look at composite properties to look at how things change across that boundary. Things like the vertical velocity, boundary layer vertical velocity from the Doppler lidar. We've also done some look at thermodynamic characteristics and started looking at aerosol trace gas and water isotope differences across that boundary. The plot here, I was, when we first made this plot, I was like thinking, that's great. That's exactly what we might expect to see. This shows the time on the horizontal axis relative to the passage of the front at the site. So 0 is when sea breeze front passes the site. This is before that. This is after that. We plotted that with respect to height here, and quantity plotted is the vertical velocity, where red colors are up and blues are down. So we see associated with this sea breeze passage, we see a very nice signal of enhanced upward vertical motion. Exactly what we would expect. That's driving cloud formation and precipitation there. Interesting, we also see a little bit in advance of that front an upward motion too, maybe associated with gravity waves that are linked to the sea breeze front passage. Okay, so those kind of give us the large scale, the synoptic scale, the mesoscale context. So now we want to start looking at some of these aerosol convection interactions and doing some machine learning techniques to try to tease apart some of the causality. So again, we're trying to deal with the fact that we have these covariant influences of aerosol and meteorology on the deep connected clouds and try to isolate the aerosol impacts, which are perhaps highly nonlinear. So to do this, first of all, we minimize the influence of that synoptic forcing by using our results from the self-organizing map study and concentrating on just the anticyclonic days. From there, we go ahead and determine what's called exposure variables. I think of this as the, or I think this could be thought of as the independent variable in your system. In this case, that's aerosols. We want to look at their impact. We have the outcome variable. This would be our dependent variable. Usually, in this case, we're going to look at ecotop height. We could discuss for a while if that's a good measure of convective strength or not, but for the purposes of this study, that's what we used. And then, of course, there's all the confounding variables. Things like the convective available potential energy, also the environmental lapse rate. We looked at wind shear, lots of the different thermodynamic and dynamic drivers that you would expect to play an important role here, both in determining the aerosol conditions and the convection conditions. And then with this, we used what's called a causal inference model, known as G computation, to estimate the aerosol impacts. And what this basically does is develops it's called a Q model that gives us a general relationship between our exposure and outcome variables, and then looks at counterfactual the counterfactual cases by inputting those into the relationship that's developed with this Q model. So in other words, we replace the clean conditions with polluting conditions and vice versa to look at how that impacts the relationship. Okay, and so applying this technique, we got these are some of the results that came out of that, where we're looking at this average causal effect is the difference between the ecotop height for dirty minus clean conditions, such that like positive values here would mean that aerosols are having a invigorating effect or a deepening effect for the ecotop height. We did find that when the CCN, if we use number concentrations of CCN for this, we did not get results that were statistically valid. So, I did not include those here. But we did find, if we look at the number of CN and ultrafine particles, that we indeed get valid results on these hatched numbers here, and those all show an increase in, or a positive number for this average causal effect, or an increase with aerosols. So with an average increase of approximately 1 kilometer. So this, there's lots of caveats in here, lots of things to consider, but it's one piece of evidence that this is showing under the conditions we're investigating here, that it suggests a potential for regime-dependent invigoration. I will note one thing we did was this combines all the cases that we observed during that time. D also separated out the sea breeze cases. And when we look at the sea breeze cases, we do see some valid results for CCN concentrations, right? And so that's interesting that would change. What that suggests, I think, is that we don't have the right, we haven't considered all the confounding variables that are going into this. For example, we might want to be considering that boundary layer vertical velocity that we observed from the Doppler lidar in our analysis here moving forward. Yeah, so that's one piece of evidence. Of course, in addition to the observational analyses, we have some modeling work going on. So this is an effort led by Steve Solivi at Colorado State, and also G-Wen Fan from Brookhaven National Lab. We're going to repeat the model into comparison project from the ACPC that I showed you in the precipitation plot before, but now using some cases from TRACER where we have all these additional measurements to help, first of all, maybe set the initial conditions for the model a little better, but be able to evaluate especially those microphysical processes. So we're looking to examine the processes that lead to, I should add, just like the model and comparison project from ACPC, we have on the order of 10 different modeling groups participating in this. So that will allow us to look at the processes that lead to the biases and the differences among those different models to maybe help us reduce some of the uncertainty in the representation of the aerosol-convection interactions. These are the two cases that we're looking at. They're both sea breeze-driven convection, but that have quite different aerosol conditions of these days. And so Steve has done some of the initial work with this, testing some results using Colorado State's Regional Atmospheric Modeling System, or RAMS. And let's see, just go right through this. He found that for the two cases, in one case he overpredicts the precipitation, the other one he underpredicts, so maybe not surprising. He finds when we do increase the aerosol loading in the simulation, so again doing a dirty and a clean simulation, with the increased aerosol loading, we see decreases in the total precipitation, the precipitation area, and the number of convective cells. And we do indeed see some increases in updraft strength, liquid water, and total ice. So this is a nice summary figure. So this is just for the one case of June 17th. Again, to normalize you, or to help you orient you here. This is the what we're plotting here is the difference in the vertical velocity composited over a simulated cell life cycle. So we've normalized the time here from initiation of a cell to the dying of the cell. Okay, so think of this as a life cycle timeline. This is the altitude, and then we're showing the difference in vertical velocity between the dirty and the clean conditions, such that red colors on here mean an increase in the vertical velocity associated with aerosols, and blues mean a decrease. So obviously there's lots of red, on there, although it's not all red. So an interesting story about where the aerosols are and where we are with respect to perhaps the thermodynamic conditions play an important role. But again, so I give all the normal caveats. This is one day, one model with one setup that we're seeing these. But another piece of evidence, a hint along the way of how aerosols might be impacting convection. Okay, so yes, results show potential for convective invigoration for modeled case and conditions. Okay, so that brings me to the end. So just a few take-home messages with my favorite picture in the background there. So yes, aerosol-convection interactions are complicated by coupling of aerosol and meteorological processes. So if we want to try to understand those effects, we need to disentangle those things. We really need to understand the multi-scale dynamics that are contributing to convection formation to be able to isolate the aerosol influences. And so we've been working on some of that, quantifying the large scale and mesoscale weather regimes. And I should say we're not the only ones doing this. Other people are doing these and taking different approaches, and we're obviously comparing those things. And our early studies suggest potential for invigoration during these TRACER cases, but of course, there's still lots of work to do and caveats and uncertainties that we need to further consider to really try to get at any cause and effect that might be going on here. And I think with that, I'll end and take questions.
Turn on the light. Anyone from students?
Students
No.
first.
So you can ask him after lunch. So, yeah.
Yeah, that's a very impressive campaign data set and measurements. I was curious about your last slide, your composite vertical figure. This is really striking. And clearly aerosols have an effect. I looked at the altitude, it's going quite high up, or at like 12 kilometers, 14. And I was wondering, what is the patch of downdraft velocity, the blue patch? Is that now ice falling out, or what is happening up there in this high altitude? Any comments or ideas? In general, the invigoration I would expect with more aerosol if there's enough water vapor. There's a lot of red, but this bluish patch is almost in the height of a cirrus under or something.
Right. So I mean, and I haven't thought too much about this, but right, that's towards the end of the convective life cycle.
Yep.
So at that point, I'm thinking, yes, we're seeing dissipating clouds. Any ties to the ingestion of the aerosol in the first place have probably happened already, and now we're to a point where we've reached some status quo at that point. So there's not much difference. That's my quick, without too much thought.
Yeah, it would be nice to have on top of that the radar or hydrometeor or some additional image on top of that to combine them to think it more 3D or temporal. I'm trying to wrap my head.
Right. I mean, right.
Yeah.
And we have to keep in mind, right, this is a composite of many
Yeah, yeah.
convective cells here, but you're absolutely right. Yeah, that should be part of it too.
What's the zero and normalized time?
Zero would be the initiation of the convective cell. So think of this, right, the timeline on the bottom is initiation to death of the convective cell. Yes, right.
Mentioned, but I mean, what about the environment? The tape, moisture. Always drawing a box around the cell and looking inside the cell. There's also ventilation. I'm assuming, I guess summertime events don't have much wind, so we don't have to worry. The hypothesis of heating, late heating, effectively there's a plume downstream of that, which can affect the environment. So it's not like, once again, this idea of a box. So I worry about how the environment changes, these
Right.
cells.
Right, I mean, absolutely, and maybe you're suggesting the other plot we should be making is the thermodynamics in a larger area around these cells. But so right, this is completely trying to isolate the aerosol impact. But I will say, we've been working with Steve and Sue on doing the same set of things with different thermodynamic environments, with saying, basically controlling, keeping the aerosol conditions the same and changing the humidity in particular. And we can make similar types of plots for that. And it's the complicated coupled system there for sure. Sure, but that's an important consideration.
So Minhua has a question online. Minhua, can you unmute yourself?
Yes, Mike. So in this picture, have you looked at the updrafts and the downdrafts separately for the difference between the dirty and the clean case?
Yes, we have looked at that some. And I actually did not include that plot because this one kind of tells the whole story, but yeah, so I don't have a good conclusion for you on that. But indeed, right, because it's model results, we could break it down into all those things. I think I've already got suggestions for 3 other plots we should be making of these composite properties.
Yeah, because that could be telling something about the role of aerosols, whether it's through change of precipitation or something else.
Right. No, absolutely. And I think as we get the simulations from the other modeling groups coming in, that those are the exact types of analyses that we'll be doing with that, you know, and looking at the diversity across the different models.
Thank you.
Thank you.
Right?
You mentioning, you mentioned like faulty position nuclei, how about like ice nuclei? Have you measured those? From those, deep clouds, most precipitation coming from ice space.
Yeah, so we do indeed have INP measurements from Jesse Creamy. So we talked about these some before. We do have those at both sites during the campaign, and during escape also they Paul DeMott was flying his instrumentation. So we have some of those. I would say we haven't looked too deeply into that yet, but we fought to get those measurements there because we knew they could be playing a role also. And your questions about how, right, in this polluted environment with very high aerosol concentrations, you know, how representative are those measurements? How do they play a role in ice formation? I think these are all things that might be things we can look at here. Any other questions?
Yeah, thank you for the presentation. Going back to your early slides, I expect you're not at all prepared to say what's happening to the aerosol indirect forcing as a consequence of your increased understanding. But if so, go ahead and say so. But you might be able to say something about how your observations relate to the Danny Rosenfeld paper.
Yeah, I mean, so I think these results were, you know, these results in the causality analysis are suggesting that maybe some of those invigoration processes that, I mean, we haven't isolated Danny or, you know, the cold or warm phase processes here. So I don't know which one yet. I don't know which one might be contributing to that, but right now, these are hinting that maybe some of those processes are indeed going on and having some impact on the vertical velocity. Say it's still early on, and I'm careful. Knowing what those meetings look like, I'm careful about saying making any conclusive things yet. But you know how that's going to impact the radiative forcing, I think that's a great question. But you know, if you are indeed invigorating the convection and moving more mass flux up into the upper atmosphere, larger cirrus shields, things like that. So you would think that it could have an impact on at least the local radiative balance, and then how important that is for the global global radiative forcing. I think we'd have to do that. Shortwave. I'm thinking shortwave most. I mean. But deep convective clouds tend to have a net zero forcing because the long wave and short wave cancel each other out. But yeah, if you're expanding the area, especially which the AMBO probably is going to have more of an impact on the shortwave side of things. You know, maybe has a net cooling effect there. That's again off the cuff right now. But I think we want to look at some of those questions, at least locally, right? Right. The field campaign this short, we're not going to be able to answer the whole radiative forcing question, but we can look at for the cases we have, what's the impact on the local radiative forcing.
Yeah, but you also can take what you learn about the physics and then apply that more broadly.
Yes. Yeah.
Because the modeling community can apply.
Absolutely.
That early slide that you showed of the divergence of all those models was I thought very, very telling.
Yes. It is, but yeah, but why? And I think one of the big things there is the higher resolution detail measurements we collected during TRACER can hopefully help to constrain those a little bit.
That would be
that's
nice
the goal.
outcome.
That's the goal, at least. Yeah.
Great. Okay, so now any further questions? That's online now. Yeah. So let's thank Mike again, so you can talk more to